we will see tomorrow. Okay. So so when I will be done, there will be this PhD student from the University of Newcastle who is going to present some preliminary results of his research, and I will introduce him to you later. For now, we need to basically go through the other type of quasi experiment that we are interested in. So we have done a difference in difference. This is a case of a quasi experiment where we have this as if randomness, which is conditioned on another variable. So if you remember, we have a quasi experiment in all the cases in which, instead of having an experiment where we are in a lab and we randomly assign a treatment to some people and we do not assign the treatment to another group of people, here we are in the case of an as if randomness, random assignment. So in this case, in particular, we are in the case of an as if random assignment where, so as if treatment conditioned on another variable. So basically the probability to get the treatment depends in case of regression. Another feature of regression discontinuity which we exploit. So this is the case in which the treatment occurs when this other variable on which the treatment depends is basically this is continuous, but you assign the treatment when this variable is above a certain threshold value or below a certain threshold value. So let's make an example. Let's assume that I am interested in evaluating the effect of attending a summer school on some grades, okay? And I make this summer school mandatory only for some people. Okay, so the summer school is the treatment. I want to assess the effect of this treatment, so attending the summer school, on an outcome variable, which is in this case the grades of students, okay, the GPA of some students, and I assume that I assign the treatment, so the ones who are actually attending the summer school are those who have performed particularly well at some other test. Okay, so let's assume, for example, in this case, that we have a y variable, which is the next year's GPA. Okay, so the performance of students tomorrow, next year. The x, which is the treatment, is the attendance of summer school. We want to estimate the effect on next year's GPA, and students are required to attend this summer school if this year's GPA is above a certain threshold value. Okay, so this means that the treatment, so whether some students receive the treatment or not, depends on whether this variable W, which is a continuous variable, okay, whether this year's GPA is above or below a certain value, W0, which we indicate with the W0. Okay, so I will be back to this figure later on, but this is the idea. Okay, so there is this treatment is assigned to those who have a condition on another variable W. Okay, so I let some students to attend the school, and these students are those who perform particularly well to some test, and there is a condition on this W above or below this threshold value, okay? So if they get, let's make an example, if you get 25, at least 25 at this exam, at my exam, then you can attend the summer school of this summer in Ventotene, okay? So there is, whether you get or not the treatment, whether you can attend or not the school, depends on another variable W, which is your grade at my exam, okay? So this is the case, the application that at which we are interested in. And whenever this is the case, so the treatment is assigned depending on another variable based on a condition which is above or below a certain W0 threshold, then we can use regression discontinuity. Okay, so this threshold value is called cutoff value, and this variable on which we base the treatment, okay, so whether or not you can attend the summer school depends on my exam, okay. This variable which is used to assign the treatment is called assignment variable or running variable or forcing variable, but we will call this assignment variable. And then what does this, so this is the case we use to apply regression discontinuity. And what does regression discontinuity do? Basically, it compares. So the aim is to estimate the treatment effect. Okay, so the effect of attending the summer school on the grades of individuals. And what does the regression discontinuity do? Compares those individuals with grades and my exam just below the threshold, so just below 25. And these are, well, in this case, these are the untreated ones, okay, in my example, to the individuals which are just above the threshold. And these are the treated in my case, because these are the ones who are allowed to actually attend the summer school. So the regression discontinuity is applied whenever we have an assignment of the treatment which depends on another variable, on a condition on another variable, whether or not this other variable is above or below a certain cutoff value. And the idea, the intuition of this methodology is that regression discontinuity compares those individuals which are just below and just above the threshold. So the intuition is that those individuals just below and just above the threshold do not have many different characteristics. Okay, so the assumption of exogeneity can be could be more easy to be applied here. Okay, so we don't want people, the ones who are treated and the ones who are not treated, to have different characteristics other than the fact that they are the first are treated and the other one are not treated. So this is what we want. Okay. And so if we take just the ones which are just above the threshold, and we compare them to the ones who are just above the threshold, then we assume that they do not have so many different characteristics other than the fact that the first one are so the ones just below are the untreated one, and the ones just above are the treated ones. Okay, so if I take, for example, you will take I don't know, 24, and you will take 25. Okay, let's assume that you go to the summer school and you don't. Okay, since you probably have the same characteristics in terms of some other variables, because you performed almost the same, okay? So you were just below and just below, just above the threshold. You were actually just at the threshold. So you probably do not have so many different characteristics in terms of other variables affecting the treatment effect. So this is what we want to estimate, okay? Then your performance in terms of GPA next year, for example, depends only with respect to you, compared to your performance, could depend only on whether you actually attended the summer school. Okay, so this is the idea underlining the regression discontinuity. So if you actually, as I said, if you perform better in terms of GPA next year with respect to R, then this difference between you and you is actually the treatment effect. So the magnitude of the discontinuity, which is the magnitude in the jump between your performance and your performance, is actually an estimate of the treatment effect if, of course, we assume that at the threshold value, at the threshold of W, nothing else happens, okay, in terms of our outcomes. So this is the example that I did before. Okay, so this is W, this is our Y, okay, outcome variable. This is next year GPA, this is this year's GPA. Then we, in this case, we assign the treatment if students are required to attend the summer school, if this year's GPA falls below a threshold. So these are the treated ones in this case, and these are the control ones. Okay, the ones who are actually not treated. Then if the difference at the threshold in the performance next year's will be actually an estimate of the treatment effect. So actually measures the effect of attending the summer school. So what did we do? This regression discontinuity design, we exploited this feature for which the treatment has been assigned depending on a condition on another continuous variable W. This condition is based on a threshold value, cutoff value, and we exploited this particular specificity to estimate the treatment effect. Why? Because those who actually have W just below the threshold and just above the threshold are probably similar in terms of all the other variables which may be confounding factors to estimate our treatment effect. Okay, so this is actually a way to estimate a clean treatment effect. Okay, so let's use another example. This weird name, Tissel, Waite, and Campbell. In 1960, studied the effect of winning a certificate of merit as part of the National Merit School. The award was given to students who actually scored more than a given score. Okay, so the award, let's try to translate this example in terms of the variables that we actually just have seen. So the award is the treatment, okay? So the award was given to students who scored more than a given score, more than a given cutoff value. So this is actually, the score is W, okay? If W is above W0 in an aptitude test, which is called CAT, then they got the award. So the assignment of the treatment depends on whether their score at this test is above a certain cutoff value. So our aim is to estimate the effect of getting the award X, so the treatment, on an outcome variable, which is the 5 years later income. So we want to estimate whether this O word is pays, okay, in terms of 5 years later income of these individuals. So basically the treatment, the O word is given. This is another way to write this condition. If W is above W0, if the score more than W0, or otherwise the probability to get the O word given W is equal to 1 if W is above W0. So, okay, so the probability of getting the O word is equal to 1. So it's certain that I get the O word if my scores at this test are above this value. And instead, this probability is equal to 0 if my score are below this W0. Then the one possibility, so if we didn't know of this regression discontinuity, was to compare the conditional mean of the 5 years later income for those who actually are awarded with respect to the conditional mean of these 5 years later income of those who didn't actually get the award. But there could be other variables. So up to now, we should know which are the issues there. So there could be other variables affecting whether I get affecting y. Okay, so the conditional mean of y with respect to the treatment. Okay, so there could be other variables like my ability, like my motivation, my intelligence, my parents' education, which are of course related to X, so are related to whether I get the award or not, because if I am more educated because my parents are more educated, then the probability to get the award is, for me, is higher. Okay, so these are correlated to the award and determine why, so determine my income in 5 years. This is a case of omitted variable bias, and we know this, okay? So even if we actually control for these confounding factors, there could be other confounding factors. So if we compare just the conditional mean of y for those who actually got the awards to the conditional mean of y for those who didn't get the award, then we probably run into an endogeneity problem. Okay? Let's assume that you get out of this master, and some of you get, so here in this university we have this award as excellent student, okay? So some of you get this excellent student award, some of you do not get this award. Then we want to estimate the effect of getting this award on your future income. If we just compare your future income, the future income of those who got the award to the future income of those who didn't get the award, we, as I told you, we are not actually controlling for other variables which may affect this treatment effect. But this regression discontinuity design, to clean for this endogeneity problem, to avoid this endogeneity problem, exploit the fact that this award is given to the ones who are actually performing well to this aptitude test. Here. To this aptitude test. So if we know that X is equal to 1, if W, if this other variable is above a certain cutoff value, then we can exploit the threshold. So we can actually measure the conditional mean of Y for those who are actually below, just below and just above the threshold. Why? Because probably there is no substantial difference between those who are actually scoring just below this threshold value and or just above the threshold value. So probably getting a score a little higher or a little lower than the threshold value is random, okay? So do not think about this example that I told you, so 24 or 25, because this could be not random, but just below or just above the threshold could be random, could be luck, okay? So if this is a way to clean for this endogeneity problem, then we can just compare the conditional mean of our future income of those who are actually just below W0, so the cutoff value. So we compute the limit of W tending to W0 of the conditional mean of Y. And we compare this to the limit mean of the ones who are just above the threshold, okay? And since this treatment has been assigned in a way for which we give the treatment to the ones who are just above the threshold, and we don't give the treatment to the ones who are below the threshold, okay, we can actually write this limit in this way, okay? So if we tend to W0 from the left, here are the ones with W below W0, so these are the ones with a score lower than the threshold value, and these are not treated, okay? So X is equal to 0. The ones who are actually just above the threshold are the treated one. So if this is the case, and this is the condition to apply regression discontinuity, then we can use the conditional mean of Y of at the threshold for those who are not treated with respect to those who are treated. Okay, so we compare what happens at the threshold, just at the threshold, for those belonging to the treated group with respect to those belonging to the control group. And this difference in the conditional mean is this jump here, and this is the treatment effect. These are other 3 examples for which the assignment depends on another variable, and this variable, so on another variable, and whether this variable is above or below a certain threshold value. You can use this later on. And we have 2 types of regression discontinuity design, which we label by RDD. The first one is the sharp RDD, and this is the case that I told you just now. So the probability so the assignment variable completely determines the treatment. So if we are below, we give the treatment, okay? If we are above the threshold, we don't give the treatment. Of course, it depends on the application. We have now done the cases for both examples. And then, so in the sharp RDD, so whether you are below or above the threshold depends only on whether you get the treatment or you don't get the treatment. So the probability of getting the treatment for those who are just below the threshold or above the threshold is equal to 1 or is equal to 0. Okay, so this condition on W determines the probability of getting the treatment. It could be equal to 1 or equal to 0. Then, if this is the case, we want to estimate, as I told you, the treatment effect when W is at the threshold value. How do we do that? So instead of estimating this model where we have the outcome variable, the treatment variable, this W assignment variable, we put here, we have here W minus its cutoff value. Okay? And this beta 1 would be the treatment effect at the threshold value for W. Okay? So we compare as before the conditional mean of Y at the threshold for those who are not treated. And if you just apply that X is equal to 0 and W is equal to W0, we are left with beta 0. Okay? To the conditional mean of Y when we are at the threshold value and we are treated. And if you just consider that X is equal to 1, this is equal to W0, so this is something that you we don't have here. So we are left with beta 1, beta 0 plus beta 1, and then we make the difference between this conditional mean and the threshold value. This difference is this one. So we are computing this jump here by using that difference between conditional mean at the threshold, and this difference is of course equal to beta 1. So this minus this is beta 1. Okay. So to estimate this model, we actually, yes, I wrote here, we use OLS of this regression model here. So this means that we control for the assignment variable. We want to estimate beta 1, so the effect of the treatment of an outcome variable. We control for this assignment variable on which the treatment depends. And we do so by computing the treatment effect at the threshold value. So we want to compute that difference at the threshold. And this is done by using this regressor, W minus W0. And then, of course, this condition, this is conditional mean independence assumption. If this applies, then our treatment estimate for the treatment effect is unbiased. We could add an interaction term. We can add non-linearities to better specify the functional form before, or so basically before or after the threshold. So we can actually, instead of having regression lines here, we can have something nonlinear. It's the same. But this is the idea underlying the sharp regression discontinuity design. And for the fuzzy regression discontinuity design, the difference is that the cutoff point does not determine, W0 does not determine whether you get or you don't get the treatment, as in the case of the sharp RVD, but affects the probability of getting the treatment. So it's not whether you are treated or not depends only on this W variable. Whether you can access to the summer school depends only on my grades, but my grades affect whether you will be able to actually access the summer school or not. Okay. And if this is the case, we need to clean for this source of homogeneity. This is just to give an intuition here. We actually apply the idea underlying instrumental variables to this case of regression discontinuity. This kind of regression discontinuity design is not really very well, very much used, but I wanted to give an intuition to you that in this case we need to use instruments which should be relevant and exogenous for our treatment variable X. And as you remember, this is the regression model that we want to estimate. The outcome variable, the treatment, the assignment variable. This assignment variable affects whether you get the treatment or not, but does not fully determine whether you get the treatment or not. How do we clean for this problem? We use a two-stage least square where we regress the treatment, which is endogenous in this case, on everything which is exogenous. So the instrument which is assumed to be exogenous but relevant, so affect whether you get the treatment, and the assignment W. Okay. So this is an application of the instrumental variable inside the regression discontinuity design. But this is something that I just wanted to report. As I said, we are not paying so much attention to this for this course, also because it's less used. And in terms of internal and external validity, these are the same as for the ones for a true experiment. So failure to randomize, failure to actually follow the treatment protocol, attrition, experimental effects, and class in the case of a fuzzy regression discontinuity design. Of course, we need to add this assumption on the validity of the instruments. And these are the same, actually the threats to external validity are the same as for the observational cross-sectional studies. Okay, so to sum up what we have done with these experiments and non-experiments, so the average treatment effect is the population mean of individual treatment effects. Okay, so we cannot observe individual treatment effects. So the population mean of these individual treatment effects is the average treatment effect. And this is estimated by the difference in potential outcomes for the, when we compare the treatment group to the control group. With quasi-experiments, we produce this as-if random assignment. And we have done the DID estimator, which allows for systematic differences in the starting values. We control for that, and these starting values, these pre-experiment values, which are different. These are different because of another variable which we do not observe, and we clean for this possibility to have another variable affecting the pre-treatment values by using this difference in difference. So we use 4 conditional means. We clean cross-section between groups. We control for between groups variables and over time pre-post treatment variables, while this regression discontinuity design, fuzzy or sharp estimates the treatment effect by at the threshold of some assignment variable. Okay, so we estimate beta 1 controlling for this assignment variable at the threshold, which determines whether you get or you do not get the treatment. But in the end, as for the DID, we estimate with OLS. Okay, so this is something that we have proved actually also yesterday with the DID. We still use OLS. Okay, so we are done with actually our the program of our course. Are there questions here? No. Okay, so now I will let Marcello start his presentation. Okay, so hi Marcello, can you hear me? Sorry, can you hear me?
Yes.
Okay, hi. So welcome. This is the class of Health Econometrics of the master course at Sapienza in Health Economics. We are around 30 people here, and we are glad to hear from you. He's, as I told you, he's a PhD at the Newcastle University. His field of research is health economics and elicitation preferences. And we are happy to hear your preliminary results on one specific topic that you actually chose for us. Thank you.
Thank you very much, Valeria. I guess I share my slides, right?
Yes.
Can you see them? Let me make it bigger.
Yes.
Yeah. Okay. So thank you very much for inviting me, and it's like a pleasure because I was an alumni of the Sapienza University, where I got my bachelor in economic sciences. So pretty nice to be back. So I'm a PhD at the University of Newcastle in Australia, and as part of my PhD research, I'm investigating the public preferences and the trade-offs, and also clearly the hesitancy for the COVID-19 vaccines and the related policy restrictions. This is like a chapter of my thesis that concerns mainly the analysis and the investigation of the trade-offs that we faced during the initial policy responses to the pandemic from policy-making perspectives, but also from the general public. So today I will have like a brief introduction about this chapter of my research, and we'll follow this agenda. So let me, if you have any questions, please feel free to interrupt me. If you don't understand some words that I pronounce, please feel free to interrupt me. So let's start from the problem. So why we wanted to pursue this research. We have seen that during the COVID-19, like effective vaccines have been developed at an unprecedented pace. They came out, they were approved within December 2020. And this is quite impressive from a scientific point of view. However, vaccines availability is not always synonym of high vaccination coverage within a country. And we have seen that this is particularly important when we look at specific countries such as France, somehow also Italy, that was forced to impose mandate to increase the vaccination take-up, and you can list other. So an essential factor for a successful vaccination campaign is the public acceptance. And we have seen that this is not uncontroversial, because in the last decades, we have seen a growing level of hesitancy and delay in acceptance of vaccines that we typically define as routine vaccines. So the tetanus, the polio, etc. And you can see this problem in the acceptance, or at least in the delay in acceptance, also for the COVID-19 vaccines. And I here reported some, I'm sorry if it's a bit small, but I hope you can see it. I reported here some data from comparable countries. I mean comparable in terms of vaccines availability for their population. So you can see that across these countries we have differences, particularly if you look at Switzerland, for example, compared to Spain. But what I want to mention here is also that Spain, even though it has like the highest coverage in terms of fully vaccinated people across all these countries, has the highest gap between the fully vaccinated people and the people that already got the booster shots. So the problem of acceptance is not only related just to the full cycle of the vaccination, but from a policy perspective, it also remains when we look at the boosters. And why is important for the booster? Clearly, because we have seen that there is evidence of antibodies waning over time. These vaccines are not able to protect us fully, at least from the risk of infection. And so there is the need for maintaining a high level of coverage to uptake boosters also in the long, not yearly, because we still don't have evidence, but at least often. We'll see with this new generation of vaccine if this is still the case, or it will change. Anyway, so from this evidence, there was the need to investigate the determinants that drive individual vaccination decisions and policy preferences to maximize mainly two main dimensions. First of all, the behavioral responses of the population, and secondly, the effectiveness of the vaccination campaigns. So then we came up with two main research questions. The first one is what features of the COVID-19 vaccines and vaccination programs are important to public opinion. Second question is, to what extent observed individual level characteristics and disease-specific conditions affect preferences for vaccination? So maybe you saw at the beginning in the title, I wrote that this is an international investigation. And indeed, it became an international investigation because at the beginning, this was just a comparison between Italy and Australia for my PhD thesis. So not very big study, but then we were able to include more partners in, and so we were able then to secure funding for 16 countries. So you can see the majority of them are coming from Europe, and we are going to administer the questionnaire in probably next week or 2 weeks, I hope. So what I'm going to discuss now is the results that we got from the piloting. Okay. So the methodology of our analysis. Probably you already saw that in the literature, there have been many studies that try to understand the willingness of the population to get the vaccines. And typically what happens is that there are questionnaires where people are asked about, like, simple question about how much are you willing to get the vaccines? And then the other questions, such as demographic, economic questions, that help researchers to then profile the respondents and see who are the groups that are more or less willing to get the vaccines. However, this simple question ignores that the vaccines being offered vary across countries, and particularly they differ in terms of some important characteristics, such as the efficacy, the side effects, the origin of the manufacturers, etc. Okay. And additionally, we have also to consider that across country, there has been a huge variation in terms of the policies adopted, and in particular in terms of the social restrictions adopted in each country. Okay, so for example, Italy had a quite stringent policy response compared, for example, to the US. So these are all factors that might affect the willingness to get the vaccines or not, and that are not captured by simple questionnaires questions. Okay. So to take into account how these characteristics influence people's preferences, we design a stated choice experiment. Now, I'm not sure how much you are familiar with this terminology and with this methodology. So we'll go very briefly through what are stated choice experiments to give you a sense of what I'm talking about. So this experiment that in health, and if you are going to pursue a career in health economics or continue health economics research, you will probably meet them under the label discrete choice experiment. So these experiments are an established technique for capturing data on preferences in hypothetical choice scenarios. Okay. So basically what it means is that people or respondents are presented with a set of scenarios that involve a choice between at least two options. And these options are described using a set of attributes with the levels for these attributes varying across scenarios. Now, don't worry if this doesn't make sense. I've reported some examples here to clarify this to you. And please, if you have any question, do not hesitate to jump in. So one example that I took from the chapter wrote by Bleemer and Rose is this one. So respondents are typically faced with a scenario. In this case, is you're looking to buy a new laptop to work from home. Okay, there is a mistake. Anyway, so which of the following laptops would you prefer? So you have then an alternative, sorry, two alternatives here, laptop A and laptop B. And you have the attributes that in this case are the processor, the hard disk, the memory in the hard disk, right? And the cost of the computer, okay? At the same time, you can see that there are different levels for each of these attributes. So for example, here we have an i5 compared to an i7. Here there is 1 terabyte memory compared to only 256 gigabytes. And then we have different costs, okay? So given these attributes and these levels, then the respondent are asked to choose their preferred option, okay? And this across different choice sets. to shift also an example in terms of like looking at healthcare setting, like one example again from the same chapter is related to choice that ask doctors to consider as the situation of a 70-year-old patient with advanced prostate cancer. So then the question is, as his doctor, what treatment would you recommend? Okay. So in this case, we have three alternatives: radiotherapy, surgery, and the no treatment. The no treatment is clearly the status quo alternative, so not doing nothing. And then again, we have different attributes, the side effects and the probability of curing patient, and then the different levels, okay? Also in this case, then respondents ask to choose their preferred option. This is a particular case because there is an unforced choice at the beginning, so people can choose the no treatment option, but then there is also the forced choice where then the doctors are required to choose between radiotherapy and surgery. Okay, if there are no questions on this, I proceed. Okay, so a key distinction of stated choice surveys is that they face, again, respondents with hypothetical, multi-attribute, and multi-alternative settings, as I just showed you, okay? So these settings allow us to disentangle the influence of different attributes that are, in our case, the vaccine characteristics on choices, okay? And then the differences in the attributes levels that I just showed you allow us also to capture the relative importance of different vaccine characteristics. And an additional advantage is also that we can capture these relative differences across people. So we can still look at heterogeneity across people, across group of people, across patients, and whatever you can think of.
Excuse me?
Yes.
Just a question about like the first one for the computer. So if you do that kind of like this kind of questions, it is so obvious that everyone is going to choose like the laptop B. So if you are doing always same questions, so what in this one, what is the result of?
Yeah, that's great comment. So this is an example, and was reported to be an example of alternative a dominant alternative in the choice task. So clearly this, as you pointed out, is clear the laptop B, the preferred option, because it's better in terms of processor, memory, and cost. So typically you won't avoid to have this comparison, and typically respondents will face at least 4 different choice tasks where these levels will change. Okay, so there will be always a trade-off that people will have to make. I just reported this example because it was quite simple and relatively easy to understand. Does this answer the question?
Okay, thank you.
So that's an example you want to avoid when you do a discrete choice experiment or a stated choice experiment, okay?
Okay, thanks.
Okay. Any other questions on these 2 examples? Okay, I'll go. Okay, just to give you a bit of background in terms of economic theory that are behind the stated choice experiments, the framework is the random utility models that you might probably already know, so I will not spend much time. Just important to underline that in these random utility models, the utility of individual n for alternative I is given by the deterministic component V and the random component, okay? So then the probability of the decision maker n to choose alternative I is given by this form, this equation here, okay? So the sum of the deterministic component and the random component should be at least equal to the utility that we get for the alternative J, okay? So to run and design a stated choice experiment is a very long process, sometimes very tedious. I listed here like the main steps that you need to follow to have like a standardized experiment, let's say. I will not go like too much into details here because otherwise it would take hours. But what I would like to do is to ask you, since like the second step is to determine the alternatives and the attributes to be included in the experiment, I would like to ask you just like, what do you think are interesting attributes for the research question that I just mentioned to you? So what are the vaccine characteristics that you think might be really relevant in the decision making when it comes to choose a vaccine, to get a vaccine for the population? Any ideas?
Like the percentage of not curing by the percentage of prevent or protecting from getting infected.
Yeah, that's certainly one. Other ideas?
Maybe for government, the price will be some attributes.
That's a great point, because typically in DCE, you typically want to include the cost or the price. However, for the COVID-19 vaccine, this might not be so relevant because most governments provided the vaccine for free. So free at the point of consumption. So for this choice task to understand the preferences, this might not be like a relevant attribute, but generally it's a very important attribute. Other ideas?
The side effects.
Yes, absolutely, very important. Others?
Attribute from the point of view of the people or from the point of view of the government?
It's the same, because at the end of the day, you want to maximize the efficiency and the effectiveness of the campaign, right? So you want to provide the best options for the consumers. Sorry, for the for the patients.
The distributions of vaccines. Conservation,
Yeah.
Distribution, or the availability of the vaccine in general.
Yeah, so availability is a good point, because it might be provided only in the hospitals, so you might need to travel a lot. It might be provided in the pharmacy in front of your house, so it's easier to access it. So that's another good option. Okay, so we can list many, so I will just go on because for sake of time. I'll list you here the ones that we identified for our experiment. So we identified 5 attributes related to the vaccine characteristics. So you can see here the efficacy reducing the infection risk, the risk of severe side effect from the vaccine, the duration of the protection, how long it has been tested before marketization has been obtained, the origin of the manufacturer, and then we also included some attributes related to the policy restrictions faced, okay, after getting the vaccine. So the social restrictions level, and whether there was or there is a mandate to return to formal or informal work activities. So that's other 2 steps that are quite technical, so don't worry if you don't get it, but it's important to determine the number of choice tasks in the experimental design, okay, and also to choose the experimental design strategy. So what we did is we designed a 36 choice task D-efficient design. The D-efficient design is the one that allows you with lower number of choice tasks to get the most of the, let's say, to get most results out of the respondent choices, okay? So it allows with lower number of choice scenarios, the more efficient results for the econometrics modeling that you're going to do for the ex-post analysis. So with just the efficient design, each respondent would face 36 choice tasks that, as you can imagine, is quite burdensome for for the respondents. Imagine to be there and like click every time for 36 times, which one do you prefer? So what typically analysts do is to divide these 36 choice tasks, or how many choice tasks you ended up with, in blocks. And we define 3 blocks. So 36 divided 3 is 12. So each respondent will face 12 choice tasks. Okay, so a much smaller amount of questions. And this is one of the examples of the choice tasks that we design for the respondents. So again, I would like to have a volunteer, or maybe 2, just to like have a sense of what will be the choice task and what respondent will face. So anyone that want to like answer this question? There is no right or wrong answer. It's just out of your preferences. So we have like the efficacy, the effectiveness in reducing severe symptoms from infection, the duration of the vaccine, the risk of severe side effect, how much time it has been spent in research and development before approval, the origin of the manufacturer, and then the level of policy restriction. So this is related to social activities, and this is related to the mandate.
I'll go for option 1.
Okay, why?
Because the manufacturer is the UK.
Okay, so that's a great example of why including this attribute is quite relevant, because there is clearly a political, not a political, but let's say a social, I would say, a social background that really lead us to choose one vaccine compared to another. And this is also very important to see how vaccine preferences vary across countries, okay? Because again, Mazzuza is,
yes,
do I pronounce? Yes, okay. If Mazzuza has a vaccine from Russia, she might not be so willing to get the vaccine, while if you can get a vaccine from the UK or even from the European Union, you might be more willing to get it immediately. Is that correct?
Yes. No. Plus the time spent on research is 24 months, so I guess it's quite good. So plus in the UK, I know the regulations are very strict. So to market some products, you really need to be like in line with regulations, so they don't play with the security of people.
Yeah. Anyone else want just to try? No? Okay, no worries. Okay, so after you design the choice task, you will come up with the attributes and the icons, as I show you. Then you test this with respondents. In this case, we tested this with respondents from Australia and Italy. So we have like 28 think aloud interviews. That is basically the same process that I did now with Mazzuza. So you go through the questionnaire and see if respondents have any questions or do not understand some indication of what you are trying to ask to them. So you can like improve the questionnaire and the way in which it's presented. And after this, you conduct a pilot study. That is the, as Valeria said at the beginning, is the stage in which we are at. So we concluded this and we are now ready to conduct the main study. But I would like to just discuss briefly the results that we got from the piloting. So the pilot was conducted in Italy and the US. We have 300 respondents in total. And the aim of the pilot to test whether the theoretical assumptions that you use to build the stated choice experiments are in line with the reality. So with what respondents actually choose. And typically what you do in a pilot is to run the most basic model that you can run with a choice experiment. That is a conditional logic model. That is always the benchmark for your future analysis, okay? So you always start from the conditional logic to then build complexities. Sorry, any questions on this? All good? So let's jump into the results. I'm not so sure about what software you typically use. From memories, Sapienza use R. But anyway, this is Stata, so it's a bit different in terms of the design of the output. But what is important here is to look at the log likelihood, which is a measure of how our model is able to minimize the error in like investigating the probability that an individual will choose option 1 compared to option 2. Okay, so what we try to do with our model is to maximize this log likelihood. That basically means make it closer to 0, as closer as 0 as possible. Okay. Another important indicator here is the number of observations. As you can see, we have 7,320 observations. And you might ask, how did you get 7,000 observations from 300 people? That is because, as I said before, each respondent will face 12 choice tasks. So at the end of the day, we end up always with a panel data. Okay, so same individuals, 12 different observations. Okay, in different times. That in this case is just different choices. Then we have our dependent variable here with the choice, and then we have the attributes. So I will not go too much in details for the interpretation of the results because this is a pilot. We have few observations, so it might be really it might overspecificate the results and our findings to go deep in this. But it's interesting to look at some the signs and at the statistical significance of these results. Okay. So let's look at the efficacy, for example. What we expect is that the higher the efficacy, the higher will be also the willingness to get the vaccine. And this is indeed what we found here, okay? So this is positive, is statistically significant, and so we can reject the null hypothesis that efficacy is not an important determinant of the vaccination choice. Similarly, for the risk of severe side effects, what we can expect? The higher the probability of facing severe side effects, the lower my willingness to get the vaccine. And this is exactly what we get, okay? So an increase of 1% in the risk of severe side effect decreases my utility. This is very important. You always have to look into the effect on utility, okay? So it decreases my utility by 27%, okay? And also this is statistically significant. The duration, again, statistically significant at the 99% confidence level, but it has a tiny, okay, impact. Again, I'm not going too much into the magnitude here because it's a pilot. Interesting, the time spent in research and development is not significant, and this is somehow against what Mazzusa was saying before, right? So in aggregate, you can see that from the pilot, how much time has been spent in research and development is not so important for the respondents in this sample, okay? Let's move to, I think, the most interesting part of this experiment, that is like how people perceive the origin of the manufacturer. So our levels were vaccine from the European Union, from Russia, from the UK, and from the US. And we have also the Chinese option, okay? But in stated choice experiments, and in general in every econometric models that you already know probably, to avoid overspecification, you have always to normalize, okay, the dummy variables, or in this case, like the attributes. So we keep at 0 the Chinese vaccine, okay? So all these sign and coefficient are in relation to having a Chinese vaccine. So for example, here for our sample, we can see that the utility that we get from having a European vaccine compared to a Chinese vaccine is positive, okay? And it increases our utility by 38%. Again, 38% is just this estimate, so do not take it as granted. It's just it's better to see the sign at this time rather than look at the magnitude. But we can certainly say at the 99% confidence level that the sample from the US and Italy prefer the European vaccine, the UK vaccine, and the US vaccines. Russia, and this is also interesting, is not statistically significant. So we fail to reject the null hypothesis that there is a difference between the Russian vaccines and the Chinese one. Okay. In terms of the policy restrictions, again, this is in line with our expectation. The higher the restriction, the lower the utility to get the vaccine. And then to conclude this first output, I would like to spend some time looking at this ask, which is called the alternative specific constant. So the alternative specific constant, as the constant that we typically have in regression output, is the value that tell me, the parameter that tell me whether everything, if like we do not have anything else considered, okay? So if we don't have all these parameters, it tells me what is the probability that responder will choose option 1 compared to option 2, okay? It can obviously tell me also other like heterogeneity, other unobserved characteristic of the choice tasks, okay? For example, one can be more, what can be like, one can be better design, okay? The icons might be more appealing for the respondents, and so it will choose more one option compared to another, okay? But it's like an estimate of everything else equal if respondents would choose more option 1 compared to option 2. And this is typically called the left-right bias, okay? And we can clearly see that this is an important component of the model because in this case it's statistically significant. So we can say at the 99% confidence level that respondents in the sample opted with higher probability for option 1 compared to option 2, okay? If we do not specify this term, we are having biases in our estimations and our results. Any questions on this?
Okay, so by saying that, it means you as a one doing the questions, so you may also put always option 1 as your preference because you know that the higher probability of choosing that, and this will bias your results. Like for example, between Russia and UK, you know that the respondent, they will always go for the choice 1. So you put UK in 1 and then you put Russia in 2, because you know.
Oh yes, yeah, no, that's clear. But like in the 12 choice tasks that people face, we use a software that combine all the levels. So you won't have always the same level in option 1 or option 2. So it will be mixed. So sometimes you will have Russian option 1, sometimes you will have Russian option 2. So like the software minimizes this bias. This is why I was telling you about the D-efficient design. That is the design that allows you with the lower number of choice tasks to maximize these trade-offs. Does this make sense?
Okay.
Okay.
And yeah. What is this software?
Engine.
Yeah. Okay, thank you.
Is produced by Choice Metrics. I mean, you can do the same thing with R and I think MATLAB as well, but Engine is specifically designed for this kind of experiments, and it's also quite easy to use. It's not free, unfortunately, but yeah. Any other questions on this? Okay. Okay, so I told you that the analysis is done in 2 countries. So one is the US and one in Italy. So basic question would be, is there any differences between the Italian and the US sample? And we can check this clearly. When you have unlabeled choice experiment, that is what we have here, because we use just option A and option B. So when you have just this like general term, you typically have the unlabeled choice experiment. The only way in which you can investigate and measure what is the impact of an individual characteristics on the probability of choosing one option over the other is to create an interaction term, okay? And here you can see that I have the same model that I showed you before, but then I add interaction terms here with the country. The country is a dummy variable that takes value 0 for Italy and 1 for the US, okay? So in this case, efficacy country would tell me how much is important the efficacy of the vaccine for the US sample compared to the Italian one, okay? And this is clearly not independent from the previous one, because this adds an information to our results, right? And you know already this, I guess, very well, so I'm not here to explain this and repeat information that you already know. So what we have here, we can see that there are statistically significant parameters here that are quite interesting, because if we look at the efficacy, again, for example, we can see that for the US sample, the efficacy is less important than for the Italian sample, okay? How do we get this? First of all, this is negative, okay? But also we can compute this difference looking at the efficacy here in the first model, right? So basically this is positive for all, but then for the US is relatively less important, okay? Same thing we can say for the risk. For the US, this is positive. That means that minus 47 plus 35 is clearly a lower amount than the parameter that we estimated before, right? So before we had minus 27 for both, now we have a minus 47, and if we look at the country, we have a 35 for the US sample, okay? So this clearly tells you that for the US, the risk of severe side effect is less relevant for compared to the Italian sample. And you can go on with this for all the other attributes. What I want to signal here is that for the US sample, the European vaccine would be less preferred, clearly, than the Italian sample. And also this is in line with our expectation. While the US is more preferred, here you can see, but this is not statistically significant, okay? And finally, what is another interesting results that we can get is that for the US sample, again, we have here a positive coefficient. That means that for the US respondents, the probability of facing full lockdown is less relevant than for the Italian sample. And this can be attributed, for example, to the experience, right? In the Italian case, we faced 2 years of really stringent interventions, while for the US, there was lockdowns at the beginning, but then was quite free, okay? So the experience and the fatigue might be an important point to consider.
Marcello, sorry.
Yes.
How do you interpret the first two results? Probably I missed this. So why for US the effects of efficacy and risk should be lower than for Italy?
Yeah, so basically, again, we have the first model here that is equal to the original model that we showed before. And then we are adding an additional term that can tell us, can disentangle like the relative effect of being a US citizen compared to the Italian. So what you do like in every regression.
This is something I understood. So the interpretation, so why should we expect that the efficacy of a vaccine should be less important in terms of preferences, in terms of attitudes for US with respect to Italy? So
the interpretation. Okay, sorry.
Yeah,
Yes. No, that's a good point. I mean, a good question that I know like a final interpretation because it's the pilot. But what I can think of is that in the US, there's been only the Moderna and the Pfizer vaccine. So they are the most effective one. While in Italy, we have, for example, the AstraZeneca one. So there may be like, again, a background experience that might give us this different perspective.
Okay.
And for the risk, again, I think I thought when I saw these results that the fact of having AstraZeneca, Pfizer and Moderna, and not having AstraZeneca, that was the one that produced the more like worries among the population, is much less relevant than the for the US sample compared to the Italian sample.
Okay, thank you.
Any other questions on this? Okay. So I said that this is like additional, like this builds complexity on our model because we are adding variable, but how can we get a sense of like how much this is improving our model? How can we get like a sense of if this variable, this information is relevant for our model and to improve the efficacy of the our estimation to reduce the error? We use typically the likelihood ratio test that is basically comparing the log likelihood for the original model compared to the new model. So I wouldn't spend too much information here, but what we can see is like the interpretation is similar to a statistical test, a t-test. So where you look at the probability of the model. So we have an hypothesis again, so that the two models are equal. There is no difference between these two models. And then you look at the distribution of the chi-square, right? So if the value is below the confidence level and significance level, you will fail to reject the null hypothesis. So in this case, we can clearly see that we can reject with 95% at the 95% confidence level the fact that the hypothesis that these two models are equal. And we can see so that adding the country variable here, the country information, improves significantly our model. We can see this also looking at the IC and the BIC results here, which are estimators that are typically used for like multinomial logit, probit modit, and probabilistic choice, let's say, models. They work as the R square in the OLS. The interpretation is different, but like for now, we can think about this, okay? So the I and the big with the second model here, you can see are lower because like the R square, you try always to have like a high R square. With the I and big, you try to minimize, okay, this score. And you can see that the big is much less smaller compared to the IC. And this is because the big by design, by construction, penalizes when you increase the number of parameters to estimate. And you can see here that the parameters reported here with the degree of freedom are quite different, right? For the original model, we have just 12, okay, this 12 here. While with this model, we have 23. So there is like a huge increase in the number of parameters, and this is penalized by the big. But again, we can reject the null hypothesis that these models are equal.
Yeah, the big is always more parsimonious than the IKT criterion. But is there, I don't know this, is there a convention on which one to use? Of course, not in this case because they were in the same direction, but is there a convention for this kind of models?
So there is not, I mean, typically use both, but because the big is more parsimonious and penalize again the fact that you're adding parameters, it depends from the model, but you might look more at the IK.
Okay. Also in time series, it depends on For example, in nonlinear models, we use the Akaike. Generally, we use the Bayesian criteria. So it really depends. Okay, so it's the same.
Yeah,
okay.
But let's say like the most, the easiest one is the likelihood ratio test. We can really just reject or not the null hypothesis. An important thing here, you can run the likelihood ratio test only if the original model that we tested is nested in the new model, okay? When I say nested, I mean that if we set all these new parameters to 0, we end up with the same model that we had before, so with the original model. If you have like cubic specification for an attribute or like other specification, you can't go back to the original model, so you cannot run the likelihood ratio test, okay, because it's not nested. Okay, just to conclude here, and then I'm happy to answer any question that you might have. Another classic investigation that we typically do as economists is to look at the differences between male and female. And so again, this is an individual characteristic. So in a lab experiments, the only way in which we can investigate this is by creating an interaction term that you can see here, okay? So in this case, you can see that for all the parameters, the interaction terms between the attributes and the variable sex is not significant, it's not statistically significant. So we can conclude that at least in this sample, in this pilot, we can reject, we fail to reject the null hypothesis that there is no difference between male and female. And this is quite interesting because typically what you have is that female are more risk averse than male, and other like common patterns. Again, this is a small sample, so it's even not it's not correct to comment it, but I mean it's interesting to look at this and see that there are no differences at this in this respect. And again, you can see that this is not significant, so that we fail to reject the null hypothesis of like sex being significant, because the likelihood ratio test here now is above the significance level that we usually use to reject or not the null hypothesis. And also you can see that the Aikagi and the big results here are much higher actually than the one that we had before, okay? Any questions on this?
No, not at all.
So just to conclude, the next steps of this research will be clearly to administer the study and the questionnaire in the 16 countries that I showed you at the beginning, to run much more complex models, such as the mixed multinomial logic, hybrid choice models, or latent class analysis. And then clearly also to look and analyze within and across country variability in vaccine preferences across like groups of people. So sex is the most common, but then there is like political view, for example, moral attitudes, economic behaviors. So there is like very much that we can do looking at the vaccination preferences choice. Okay, any questions in general?